Okay, now we have a more difficult video this time. I know the previous one took 2.5 hours for me to solve, and I expect all of these to take me quite a while to make any progress on. But I think this one's going to be a bit less than anticipated. I think this one's going to be a solid plan. Um, so, basic rules, Sudoku rules apply, killer cage rules, and little killer clues. Simple as that. And let's go. Well, first thing I see is this is a pretty high value for a diagonal like this. The values are there: 7 to 55. 7 goes to 56 8 times. So the average of this is a little bit less than... It doesn't include a 1. It can. It can include a singleton 1. Because if that's a 1... No, it can't. Because then that would all have to be 9s. 9, 8 makes 15. 9 makes 24. 9, 8 makes 39. 9 plus 1 is 49. So there cannot be a 1 along this diagonal. Okay, that's a good start. That's kind of interesting. Actually, that's really interesting. Is this going to be like a set puzzle? Okay, so, and this. How much does that add up to? All of the outside values, so 26 plus 47 plus 30 plus 41 plus 23 plus 55 plus 11 plus 49, 282. Oh. They've used the Fistmofel ring. Okay, so this, with Kenny these twice, is all of this. So now I have plus 19 plus 20 plus 13 plus 19 equals 353. Then I do it again. Plus 19 plus 20 plus 19 plus 13 means that all of this equals 424. So I'm gonna put purple in all the ones I've counted once. Oh, wait a second. So 424 plus 90 is 514. So these cells counted 3 times. No, 4 times. Because this is diagonal, that's diagonal. Those were counted. Those were already double counted. So these cells 4 times, and that cell twice, adds to 514. Okay, so I'll copy 514. 45 times 9 is 405. So the difference is 109. So if these have to be different, maximally they could be 9-8. Maximally those could be 9-8. So given that they all add to 109, 9 plus 8 is 17. Times 4 is 68. Times 4 is 272. So these maximally add to 272. No, wait a second. This is 17 divided by 2. 272 divided by... Sorry, that's a 68. Okay, so wait, these add to give you 17. Times 4, because kind of quadruply, is 68. Times 2 is 136. So, yeah, these are each counted 4 times. So we've got 8 plus 9 plus 8 plus 9. So if these are all 8, 9 pairs, they add to 34. And I've counted them once, twice, 3 times, 4 times. So 34 times 4 is 136. This was counted, so it's lower than this then. Okay, so I got 109. What values? Well, no matter what, we know that this has to be odd. No, wait a second. 109? Are there other cells that I'm missing in this? Those are the only cells that... See, I got 109 as a difference. I got 514. Well, I can add I'll add it up all again. So it's 26 plus 47 plus 30 plus 41 plus 23 plus 55 plus 11 plus 49 plus 19 plus 19 plus 20 plus 20 plus 19 plus 19 plus 13 plus 13 equals 424. What did I miss? Oh, and then the 2 lots of 45 plus 90 gives you 514, and it should be 405. So yeah. Oh wait, no, because if I subtract 1 from all of this, I understand now. Okay, so now I subtract 1 whole board, 409. So now these are now times 3, and that's just once. Okay, 109. 8 plus 9 is 17, so that's both of these add to that. Times 2 gives us 34, so those have to be 34. Times 3 is 102, and that is only counted once. It has to be a 7. These are 8 9s, and that's a 7. Cool start. Interesting start to a puzzle. I also realized that here there's 11s. So this could be 1, 1, 2. Okay, does that actually not have any... Does this need to have a 1 in it? 2, 2, 3, 2. Nope. Does this need to have anything in it? 2, 3, 4, 5, that's a 14, so this needs to have a 1 in it. Which means this can't have a 1 in it. Whoops. Which means this has to be minimum 2, 3, 5, which means this has to add to 6. Yeah, so this could be... This could be, what, 1, 3, 4, 5? Yeah, because it can't be 2, 3, 4, 5, because that adds to 14. So it needs to include a 1. So that means that the other ones add to 12. How do I make 12 with 3 digits? A million different ways. 7, 3, 2. Hell, yeah, okay. Oh, this seems like it's an interesting diagonal to work upon. Oh, wait a second. Nope, I was going to say that, like, this has to be shunted down in here. Because you can't put an 8, 9 in a cage with a 1. Because if it's a 1 plus 8 is 9, the other two have to be a 1 and a 3 in order to make it add up. So even if this was an 8, this would add to 9, the other one has to add to 4, which can only be a 1, 3, and we already have a 1 in there. So this is the same as this. And this is the opposite of this. Which means that this and this have to be different. So here we go. We got the parities. We know that those two are the same digit. Okay. And then green has to go here. Aha, wait a second. Green has to be shunted up here. And purple has to be shunted in here. And then once again, there's a possibility we could shunt a green or purple in there. Yeah, we can't shove either of them in here, so they have to go on the sides. You can't put an 8 or 9 anywhere there. Because you put an 8 or 9 on an 11 cage, even if it's an 8, 1, 1, 1 would be necessary, and we can't do that because of the ones here. So neither of these can be that. So this is an 8-9 pair. That's an 8-9. Greens can't go there. Purples can't go there. Cool. This could definitely be 8-8-8 with no issue. We're still no further with this 11. Let's work on the 19s, maybe? Oh, well, we already knew that there had to be... Oh! Fistamafel ring. There has to be a green up there, but there can't be a second green. There has to be a purple in here, but there can't be a second purple. Could it be a green and a purple one of these cages? 19-2? No, there can't. So we need to have both a purple and a green up in there in order for it to add up correctly. Because we don't have a purple or a green in there, we need to have 2 purples and 2 greens in these cells. So you need to have a purple-green here. Which I'll mark as just a blue. That cell doesn't need to be colored. That's a really... I like that way to start the puzzle. That was neat. I like seeing those kinds of set diagonals. I kind of just saw it by accident. I'm like, oh, these kind of like line up weirdly, don't they? And then I started filling in the rest of the cage, the rest of the puzzle. I'm like, oh, that's pretty neat. And then from there, I was like, wait, what's missing? Oh, wait, there's like all of these cells that are missing, and those are doubled up upon. That's really cool. Okay, well. Oh, okay. Wait a second. There has to be a purple in here. There can't be a purple there. There can't be a purple there, so one of these is a purple. Well, actually, no, the purple has to be here. Because we can't have a purple in there, because we can't have both a purple and green. We can't have purple here, so there has to be a purple there. Okay. Likewise, you know there can't be a green in here, because it just wouldn't fit. There can't be greens there, so that has to be a green. So yeah, that's another way of showing it, that there's a green, there's a green. And likewise, there's the purple, there's the purple. So there has to be a purple and a green in here. Which also means this is a 1, 2, 8, 9 pair. Cool. These guys are interesting to me, that they go along the same diagonal. But otherwise, not too much else. Just a minimum of 2 and 3. So if that adds to 2 and 3, then this needs to be sub to 6. It could be a 1 and a 5. A 2 and a 4. Which they're all fine to do. No issue. 1, 5, 2, 4. So I don't think we can put the... okay, well, let's see. First of all, green can't be here. If green was here, then this would be 16, 17... Oh, no, you totally could, couldn't you? 18. Damn. Wait a second. That adds to 17. This adds to 13. These cells had to add to 15 without 8 or 9. 5, 6, 7 gives us 18, so we only have 3 degrees of flexibility. So if we go low, 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 we could have, if this adds to 15, this can't be a 1. What's the lowest this could be? If this adds to 15, that could be a 7. That's the highest number that can be. So then if that adds to 15, then that could be, that has to add to 8. Which means these two add up to 3. Means it's a 1-2 pair. They could still both be 1s. If this is so, this has to be a 7 or a 6 or a 7. Yeah, because no matter how I built this, if this was a 7, this adds to be 8, which means these need to add to be 3. Yeah, so if this adds to 6, these are both 1s. Yeah, which is fine, because if it adds to 6, then this adds to give you 9. We can't have 8, we could have 7, 2. Yep, and it'll be 6, 7, 2, and that would work. With both those being 1s. And it maths out. Cool. Are there any other... These evals aren't used by anything else, though, so I don't actually find anything too interesting. That adds to 27. Is there more set theory maybe I can do? I think there is a 6, 7 somewhere. It doesn't really help me very much. If there was a big number over a short diagonal, or another small number over a long diagonal, that might be helpful. This is 47. Can that add... So what happens if I add that together? So let's just assume that it's 9. Then the rest of those values I have to give 20, which is super easy. Or they can add to give you 24, or 23. Which is a tad harder, but still super easy. Huh. Okay, so this is definitely something to do with sums. It's a something. It says an 8 or 9 in it. And the other cells have to add to like 11. This can't be 8 or 9. This has to be a lower value. Let's highlight every row and column that can, or every cell that cannot have an 8 or 9 in it, and we'll label that red for now. Just see what we get out of it. See if we can see any interesting patterns. So I know there's 2 greens here. Cancel out greens from there, but we don't have any purples to work with, so I can't exclude anything particular. And notably, these diagonals seem to pierce through all of that. This is interesting, though. 7, 6. Adds to 17. Which means if these are 7, 6, these have to be 9, 8. And if you drop them down to 7, 5, then you could theoretically add a 7 there. Those are still really restricted. Aha, now we're getting somewhere, because now we're getting 6, 7s on the board. Can I restrict with this, maybe? Yeah, suppose that this wasn't 8 or 9. Well, no, we can't... Well, yeah. Suppose that this is neither 8 or 9. Suppose, theoretically. No, because we need to have them high numbers. Let's suppose this is... Oh, no, because it could just be a 1. This is... odd. Yeah, there's not a lot of helpful values here. Besides those intersections, which we know are 8, 9s. Maybe it's another, like, do this. What do those cells have to add up to? Yeah, because we know that they use opposite 8 nines, so we know that it's 17 times 3 gives us 51. So 55 plus 47 minus 51 is 51. Okay, so these cells have to add to give us 51. 3, 4, 5, 6, 7, 8 cells. This could be a maximum of 9. 42. These could be 8 nines. Minus 17, minus 17. These could also be 8 nines. So you have 9 degrees of flexibility to work with. Ah, crap. Well, this would have to be purple, which makes this green. This would have to be green, which makes that purple, and there's no issue. Yep, there's no issue. Of course there isn't. Because if that's a green, then that's a green, there's no conflict. Purple means that's purple, no conflict. And with that being purple and that being purple, yeah, that has to be purple, which would make that purple. Yeah, but even still, we're only knocking it down another order or two. It doesn't really do very much, like by 1 flexible degree. I don't quite see how to continue from here. I mean, besides, like, I'm done the fist of Eldring for now. Like, I don't see anything else that really benefits. Oh yeah, I guess I just do 3, 4, 5 here. Actually, that's kind of low on the 47. Yeah, so this is a 7. What can those values be? We have to add to 8. So we've got 6, 2, and 5, 3. Doesn't really help anymore. Well, let's do this again. What's the minimum that can be? 8 plus 8 plus 8 plus 3 is 27. Can we get those 3 values to add to 20? Nine, 9, 9. They can go to 27. Ugh, come on. Excuse me. Maybe it's the corners again. I don't know. I'm trying to figure out what I could possibly do here, but can this be without a 1? Yeah, it can pretty easily, can't it? This is 9, 2, 3, 6 or something. Ay, 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 Dios mío. Well, we can at least figure out what this sums out, what this sums up to directly. Because we know that that's 41 minus 17, period. 24 over 5 different digits is absolutely nothing helpful. This all average a little, like a slight bit below 5. Three digits adding to 18 is nothing special. Let's suppose that all those are there. 49 minus 17 minus 17 means that these values have to add to 15. Which again, average of 5 tells us nothing. I think I saw the initial break-in, but I haven't been able to make an inch of progress since. Or wait, could it be like do this again kind of thing? So this is 26 plus 47 plus 30 plus 41 plus 23 plus 55 plus 11 plus 49. And they double up on 8, 9. They use it twice for each of them. So it's 37, or 34 times 2, so minus 68. 214. Okay, how many cells is this? 16, 17, 18 makes 36. Slightly above 5. Does not help. Could these both be 2? No. They can't both be 2. So no matter what, that can't be a 1. Hey, progress, I guess. I don't know. I don't know how to make any progress here. Kind of drawing a blank. If this is a 1, that has to be a 1, which means there can't be any 1s here.
New studies available on Prolific.
If this is a 1, then one of these has to be a 1. If this is not a 1, then this has to be a 1, meaning one of these could be a 1. So these cannot contain more than 1 1. Wait a second. Okay, wait. If these are both 1s, then those are the only places where 1s can go. For the Fistmafel ring. And there has to be 2. So yeah, if these are both 1s, then those are the only places where the 1s can go on the Fistmafel ring. Because if they're both 1s, then they exclude all of these, and then these based on being in the same square as them. So those are the places where 1s can go, and that's only 2 rows, so that means that none of these can have 1s. So if these are both 1s, obviously none of those can have 1s, but then we've locked in down to 2 different cells per row. But none of these actually hit the 1s. That's annoying. Ah. This is a 1 and a 2. Let's just do a little bit of math here. Then I can just put two up there and a 1 down here, and there's absolutely no issue. Gosh. I have no idea how to inch. Could that be a purple? Probably. Oh, but that's a maximum of 5. So 50 minus 5 minus 9 minus 9 minus 9 means that these have to give me 18. These have to be a maximum of 7. And that's a maximum of 4. So, given that well, that ends up with being a 4, but it could be a 9. So I got 5 degrees of flexibility left to play with. What about this diagonal, though? By that same degree, because that's lower. So what's the highest that it can go? 5. Sorry, the lowest it can be. 5 plus 8 plus 8 plus 8 is 29. So then these are a minimum of 18. That's a 7. 7 makes 14. This has to be at least a 4. 5 degrees. If I maximize these, I put them all to the highest possible value. 5 plus 9 plus 9 plus 9 is 32, which means these have to add to 15. These can only be 7, which means that has to be a 1. So that would imply that all of these are 9s. These are both purples. That's a 1, which means that's a 2, which means that's a 1. Yeah, so let's actually just play out that bifurcation for a second. 5. That is what needs to be done in that circumstance. Ah, wait a second. No, we only have one. So wait, if I do 5 plus 9 plus 9 plus 9 plus 8 plus 8 plus 1. No, plus 9 as high as we can go. Okay, so we have a lot of degrees of freedom here going down. But it's going up with a minimum that we do have restriction on. 3 plus 8. Whoops. Plus 8 plus 8 Means that these have to add to 20. So 9, 9, 2. Yeah, it's doable. I'm gonna come back to this. If those are both ones, does anything bad happen? These add to 9. Which means this adds to 6. So if it was 1, 1, 6, like this, then that would be a 1. That will be a 1. That will be a 1. That will be a 1. I don't see any progress I can make here. I'm saying nothing because I can't think of anything. Like, can these can be 5s, right? Could these be 5s? 7 plus 5 makes 12. Those can be 9, 9. No, they can't be 9, 9. Because they see both of these at the same time. So that has to be 6, 7. Which means no matter what, we have 30 minus 13 is 17. So these can't be 7s. There we go. Okay. Progress. Okay. Progress, progress. Blue means both. Cool. A little bit of progress being made here. A little bit, little bit. That means that green has to be over there. Purple. Well, this is both green and purple, so that can't be green or purple. Ah, this and this is guaranteed. Oh no, so this is guaranteed. This is guaranteed. One of those is guaranteed. Means those are the possible greens. Otherwise, that is purple. Yeah, so... Sorry. That is purple. That is purple. These are the purples we're working with. Okay. Which means no other cells can be... So this has to be a maximum of 7. So let's maximize these cells then. 5 plus 9 plus 9 plus 9 plus 7 plus 8 plus 8. This is 55. Oh, wait. Yeah, let's maximize those cells. 9 plus 9 plus 9 plus 8 plus 8 plus 5 gives us 48, which means that if I'm maximizing the cells, that has to be a minimum of 7. We have 1 degree of flexibility. Since we only have, in this case, yeah, that's it. That's it. It has to be like this. Because it doesn't work otherwise. If they're any lower than that, then you drag yourself away from it. You need to be to be an absolute maximum. So this has to be 8, 9. That has to be 8, 9, which means that's the only place that could be purple. Cool. And now that has to be 8, 9. Cool. Okay. This we can't find nearly as strongly, but we know that that can't be 5s, which is nice to finally figure out a little bit. The maximum here is 4. Oh wait, so actually we know that this has that purples have to be 9s and greens have to be 8s. So what's the maximum this can be? Well, it's 8 plus 8 plus 8 plus 4. That's a 28 minus 47. So that these add to give you 19. Yeah, so that doesn't help too much. So this is it is 19 or 20. Oh, this is a 6. One of these has to be a 7. Eight plus 8 plus 8 plus 9 plus 9 plus 3 gives 45. So that would have to be a 2 or a 1. Yeah, that would be a 2 or a 1 if that's a 4. So those are both purple. That's a 1, 2, but it could be lower than that. And they don't have to be purples. Oh, what about this 49 diagonal? First of all, we know that this is an 8. So this 49 diagonal is really interesting. Because we have 49 minus 8 minus 8 minus 9. Which means you know that these add to give us 24. Which means not all of these can be 9s. In fact, this can't be a 9. And that gives you 18, and that has to be a 9 to be 27. So that can't be a 9. Ah, and these can't both be 9s either. Because if they're both 9s, they exclude both the other possibilities of being 9s in those cells. So if this is a 9, then it has to be a 9. If this is a 9, then that can't be a 9. If that's a 9, then that can't be a 9. Can neither of them be 9s? No, at least exactly one of them has to be a 9. So we have 8 plus 8 plus 9 plus 9 gives 34, which means the other leftover cells have to add to give 15, which is an average of 5, which doesn't help. At least we've caught out one broken cell. That's something. That's a little start. Yeah, one of those could be a 9. If I could somehow exclude one of these, because right now this is like an angled duo. So this, or this. Could these both be 9s? 26 minus 9 minus 9. Yeah, because then these both would have to add it to give you 8, which is low enough that I could do with... Yeah, so 7-2 would work. Sorry, 7-1 would work. 6-2 would work. Yeah, it'll keep going. 5-3 would work. So those could both be 9s. Because then you'd have this as the other cell. Are there any other diagonals that go through a bunch of weird values? That's a reasonably low number for that diagonal. 41 minus 9 minus 8. So these add to give 24. If I subtract 7, then these have to add to give 17. Which, I mean, they can fairly easily. They only average a little bit below 5. Oh, this would be a bit more restricted, but it isn't. So I'm just going to do this a bit better. That has to be one of 8. This has to have an 8. One of these have to have a 9. Okay, there we go. None of these can be 8s or 9s. 7 plus... So yeah, this could be a 7, this could be a 6, and this could be 6-5. That's 24. 7, 6... If you do it like this, that's 1 off. So we only have 1 degree of flexibility here. Okay. That's 5. That's 4. That can't be a 5, so that has to be a 6, no matter what. This could be a 6 as well. Okay. That's a bit of reduction done. A little bit further. 6 then has to be in this column, so one of these has to be a 6. That was a good find. Good find. If neither of those are 9s or 8s, then this is reasonably restricted. Because then this would have to be 6. This would have to be 7, 6. And this would be 7. That's a maximum. So yeah, if these are not that, then this is locked in place. Is there any contradiction with having those selected as our 9s? There's got to be something. Come on. Come on. Okay, so let's just suppose that those are 9s. This has a minimum value of 7. This can't be 9, can't be 8, can't be 7, so 6. That can't be 9 or 8 or 7, so it has to be 6. This can't be 9 or 8, but it could be a 7. So this adds to 8 plus 9 plus 8 plus 7 plus 6 plus 6 plus 7 is 51. So we only have 2 degrees of freedom here. Can we knock them down anymore? If that's a 7, then that's a 6. Oh, sorry, no, this is a theoretical 9 here, rather, sorry. Oh, wait a second. 7 plus 6 plus 8 plus 9 plus 9 plus 7 plus 8 is way higher, right? 54. So we have 5 degrees of freedom along these numbers here. Oh, gosh. Yeah, 5 degrees is too much for me to be able to work with, unfortunately. Whoops. There we go. Actually, if I chose those as my 9s, this is a minimum of 6, or maximum of 6. That's a maximum of 6 again. That's another maximum of 7. What does that give us? 9 plus 6 plus 8 plus 6 plus 9 plus 7 plus 8. 53. So only 4 degrees of freedom here. Which is something, but not really. Ah, rip. Well, if I have these as 9s... Yeah, so if I choose like this, so then it's got 8 plus 8 plus 8 plus 9 plus 9 is 42. So this has to be a 1-2 pair, which is totally okay. Ah, crap. If I can force this to be a 7, then I can do something with it. So I think that this might be where I need to explore on the 1s and 2s here. Because if that's a 7, then these both have to be both... Oh no, they have to be a 1-2. If they're a 6, then they both have to be 1-1. Can I show that they can't both be 1s? No, I don't see any way that I don't see any way that I can disprove that. Oh, wait a second. This is 9. That might actually be a slight change in something if I wasn't paying good enough attention. That's a 9. Could this be 9, 8, 7, 6? Just leave 5, 4. Which means that's a 1, 3, and that's fine. Crud. Ah, wait a second. These had to be... This is 19, and there's already a 9 in here. The other 3 have to add to 10. So we can't have a 7 in there. Ah, we can't. It would be 7, 1, 2. Okay, so let's theorize this for a second. Oh, I don't think you can do it. You can't do it. Because so if you want to have a 9 and a 7, so yeah, let's suppose that this is a 7, then that has to be a 9. Okay, you need there to be 1, 2, and you need there needs to be a 1 and a 2, which you cannot do, because if that's a 1 and 2, you break this. So this can't be a 7. Okay, can this one be a 7? If that's a 7, then there must be a 9 up there, which means all of this together gives you a 1, 2. So this is our 9, 1, 2. This is 9, 1, 2, which means this can't be a 1. I mean, there has to be a 1 up here, which means a 1 can't be down there. So that has to be a 1. That has to be a 2. Any issue with this? Yeah, if that's a 2, then if that's a 2, yeah, so then they can't be both be 2. It was either both 1s or like this. So, sorry, whoops, then this has to be a 1. Crud. Which means that's a 1. A 1 somewhere up there. This has to be a 2. So 1, 2, 2 makes 5. That has to be a 6. Which it can't be. Yep, because there has to be a 2 there, has to be a 2 there. That's the only other place that a 2 can go. Which means that would have to be a 2. Which it can't be, because now that adds to 4. Because that's 7. 7 plus 13 is 20. 20 plus... that's 37. Which means this needs to be an 8, which it can't be. Which means we showed that this can't be a 7, because that's the only actual assumption we had here. Which means this is a 7. Which means this is a 6. Which means these two add to give us 9, which means these are both 1s. Yep, so this guy has to give 9 now. We've got 2, 7. So yeah, let's actually put in the possible values. There's 2, 7 is one of them. Then we have 3, 6, which you can't do. 4, 5. Those are still both available. So then we have to have a 3 here. Which means that these other ones need to add up to 9 in the very same opposite ways. 3, 4, 5, 6. Yeah, okay. This can't be a 7, though. So that can't be a 2. So it should be like this, sorry. That's what I meant to do. I goofed up, I did it backwards. 6 has to be down there somewhere. This maximally 9, 8, 7, 6, 5, 4. 9 plus 5 can't be both 5, 4, so 9 plus 5 plus 3 is 17. Plus 2 is 19. That's a maximum you could possibly have in here. Because, yeah, if you have 9, you can't do 8, 7, or 6. You can have a 5, but then you can't have a 4. 3, 2, that adds to 19. That is the highest you could possibly have in there. Which means this is a 1. Which, I mean, we already knew, but... and by that extension, that has to be a 4. Cool. 1, 2, 3, 4, 5, 6, 7, 8, 9. Cool. Which means that's a 6. Cool puzzle. This this is a very, very tricky break-in, I will say. This can't be a 5. One, 2, 3, 9, 4. I was like, I see 1, 2, thing, and I could not piece together what the missing number was, but there we go. It's 4. 1, 2, 8, 9, 5. 3. 1, 2, 3, 5, 8, 9. Can't tell what those numbers are. So 1, 2, 3. Which means neither of these can be a 1. Neither of those can be a 3. That's 2, 8. Okay. Neat. We have no values about 2s, no value, like no more information about 8s or 9s. But we've made progress. We made a dent. Okay, let's keep navigating this dent. These values haven't aided on this diagonal whatsoever. Did they add on this diagonal? No. But they added on this one. Okay, let's punch it in. 41. Let's maximize it. Minus 7, minus 9, minus 8, minus 3. This needs to add to 14. Or 2 higher. 16. Either which is no issue. Oh, what does this add up to? Here we go. 6 plus 6 plus 4, 16. You need to be a 7. That's a 7, that's a 6. Okay. Which means one of these is a 7. Neat. One, 2, 3, 4, 5, 6, 7, 8, 9. So 2, 3, 4, 5. That can't be a 4. Which means that can't be a 5. Has to include a 4, which I mean we already know because of that. Which this includes has to include a 4. That has to be a 7. Which means that's a 2. That subtracts a 2, which means you subtract the 3, 5 here. Let's go. Okay. This includes a 2 and a 4, which means 2 cannot go here, which means 2 must go there. Okay. 4 can't go there, so one of these needs to be a 4. That doesn't need to be a 7 anymore. Whoops. So what values need to go in here? 1, 2, 3, 4, 5. Makes 12. 6, 7, 8, 9. No, that's wrong. No, it's right. Because it's 12 plus 1, right? Gosh. Okay, yep. So that means that this has to be a... That's right, not 4, 5, 6. Oh, crud. 3, 4, 5. Okay, here we go. That can't be a 4. So 4 needs to go down here. Still doesn't aid on this diagonal, though. Like, these values aren't at all being touched by any of the diagonals, so they don't actually get me very much. Yeah, so I don't really get any mathematical progress here. Oops, sorry. Mathematic, 1 goes there. Okay. That's down to 11 without a 1. We're now down to only 3 possible degrees, which means this has to include a 2. So so this has to 11. So when we got rid of the 8, we have to 11. Without a 1, because it can't be a 1, it's 2, 3, 4 is the minimum, which is 9. We need to get to 11, which means we have 2 degrees of freedom. So either at 2, 3, 6 or 2, 4, 5. Either way, included 2. Which means by that extension, this also includes a 2, so one of these needs to include a 2 here. By that extension, this has to include. So we've got 2, 8. And now we have the last digits of 19, means we need to add to 9. Can't use a 1, can't use a 2. So we've got 3, 6, 4, 5. So it's either 3, 6, which 3s are there, or 4, 5. In which case, with 4, 5 here and 4, 5 here, we're guaranteeing a 4, 5 pair there. But, because of this, 2 has to go here. Which means it can't be a 4, 5 pair. Which means that can't be a 4, 5 pair. Which means it needs to be a 3, 6 pair. So it's 2, 3, 6, 8. That adds up correctly. I'm pretty sure that's mathematically sound. 2, 3, 8. We're almost there. Well, that has to go in one of those 2 places. We already know that. What else do we know? 1, 2, 3. Where does 4 go? We know it's in one of those 2 spaces, so it could go along the side here. 2, 3, 4. So 6, 8 means we're looking at 7 as well. 7 has to go down here. So this is a 7, 9 pair. Which does actually restrict this a little bit. So we are either looking at 7 something or 9, 9.
New studies available on Prolific.
So 26 minus 9 minus 9 means the other 2 have to be 8. But if we do 7 plus 9, then they have to add 10. Never mind. Okay. 7 plus... That's not 9, that's 7 plus... has to be 6. 7 plus 6 is 13. So can these both add to be 13? Well, that has to be 4, 9. Well, it can't be that. Could be 5, 8. Can't be that. Could be 6, 7. This can't be a 6 or a 7. Because that's a 7. And a 6 is in here. Which means these have to both be 9s. Which means that's a 9. Thank you, diagonal. Now those are going to be tricky to solve. We managed to solve because it can't be anything except... Okay, now let's work with here. 7 plus 8 plus 9 plus 9 plus 8 plus 4 as a maximum means that this is a minimum of 4. Or 6. 4 or 6 are the 2 possible answers. Some contrast with this. Threes. 2s and 3s can't go there, so they have to go here. Which means that has to be a 7. 1, 2, 3, 4, 5, 6. That's gonna be 5, 6. Which means 4 can't go anywhere else except for there. Hello. Which means 4 goes there. Which means 4 goes there, 2 goes there. There has to be a 5 here. There has to be a 5 there. Well, we already know this has to be a 1, 5. What was it? 1, 5, 1, 4, 5. Okay. Yeah, so it's gonna be like this. Like, so I think it's gonna be this cage resolves this cage, which resolves this cage, which resolves this cage, which resolves this cage to break up everything there. I mean, this cage will probably also resolve this cage, but same idea. Like, it's going to be spiraling in that direction around the board. This is 1, 2, 3, 5, 6. Five, 6 have to both be up there. Because 5, 6 can't be here. And they can't be there, so they've got to be there. Which means that's a 2. That's a 5. That's a 3. I was wrong. I thought that would resolve differently. Oh, well, it resolved this, but it doesn't resolve the rest of this because it's horizontal. This needs to be resolved. I mean, this could be resolved horizontally here, I guess. One, 2. So this is a 1, 2, 3. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9. It's going to be a 1, 5, 6. Because of that, this can't be a 1. Which means this has to be a 1, because it's the only place it will go. And that adds up correctly. Okay. Sub 90 minutes. Let's see if I can beat his cracking the cryptic score. Well, this can't be a 5. So this is 3, 4, 2. This is 1, 2, 3, 4. Yeah, that's all that they are. So it's 1, 2, 3. And we have no value about this. Okay. Let's work on this diagonal again, now that we have those values restricted. 26 minus 9 minus 9. So this is so this has to be 8 minus this. So it's either 7, 4, or 3. Those are the only possible options for that. That's a 4, then that's a 4. Cool. Then that's a 4. Things collapse. If that's a 5, that's a 3. That's a 2, that's a 5. That's a 1. That's 6. That's whatever's left over. Actually, that might be a line of thought. If that's a 3, that's a 2, that's a 3, that's a 5. We don't have any 2 values anywhere. That's the issue, okay. That's a 7, that's a 1, that's a 4, that's a 3. 2, 3. Pair. Each of those. Okay, yeah, those are 2, 3. Okay, so this can't be a 7. Which means that can't be a 1. So that's a 7. Then it collapses and gives us 2, 3 pairs here. And since we know that one of these, that we have these down here. So if this is a 4, then this is a 3. Oh, wait a second. No, I did that wrong. If this is a 4... Oops, sorry. For whatever reason, if that's a 4, then that's a 3. Which means that's a 2, which means that's a 1. Makes that a 3, which makes that a 2. Makes that a 5, which makes that a 3. So it's just 5, 6 pair. This is a 6. This is a 5. Be a 1. 1, 2, 3, 4, 5. That's a 6. Maybe that'll work. Looking for a contradiction, so I'm not going to follow down that line of logic any further. I didn't realize there was a 6 down here. That with oopsie. There's a 1 actually over here as well. Ah, wait, where does 7 go in this column? Can't go there, can't go there, can't go there, can't go there. So that's 7. That is a 7. Which makes that a 1. Which makes it a 4, which is I was going down the correct line. I just didn't get the initial start. Sorry, 3. 1, 5. So that's a 5. That's a 6. Makes that a 1, 6, 5. 1, 1, 2, 3, 4, 5, 6. 3, 5. Come on, crack. 3. Instead of 4. 5. Oh, you're not giving up? Come on. Come on, crack, crack, crack. Man, it's so close to giving. I just can't quite tell what I'm missing in order to get it going. Where'd I put 1 in that row? Has to be there. That has to be a 5. Wait, sorry. That can't be a 5. That has to be a 3. Looks at a 5. No 3s. That has to be a 6, which means no 6s. 2, 3, 8. 2, 8, 9. The 3 has to go there. Ah, come on, come on, come on, come on. Come on, just collapse. Where does 4 go in this column? Can't go there, can't go there, can't go there. That's a 4. Oh. Come on, is that not sufficient? Is that actually not enough? 3, 5, 6, 8. Oh my gosh. 2, 6, 8. 2, 3, 9. Oh, wait. Neither of these can be 9s. 2, 3, 5, 9. Oh, come on. it's teetering. Just barely isn't giving. I filled in everything else except for these two cells. Did I miss something about this diagonal? Is there a diagonal here that hits those cells? Of course there isn't. Okay, I don't want to do more bifurcation, but I'll just do... Ah, 2, 3, 8. I missed there was 8s. There was already 8s in this column? Two, 3, 6, 5. Oh, I'm 8 minutes away from sub 90, which was the goal for this puzzle, but I just barely can't quite crack it. I don't want to bifurcate here. I want to just analyze and actually get something here. Like, this is really interesting. The 289 here is really irritating. Wait. God damn it. I don't understand, like... I finished it, but this was just bifurcating towards the very end. There might be more than one solution. That's my issue. So I said that was a 3. What's the issue if that's a 5 instead? That's a 6, that's a 5. Oh my god, am I blind? There's a 2. That make a difference? Cyclic. 2, 3, 6, 5, 8. Okay, so this can't be an 8 either. I'd be missing numbers left and right. That can't be a 9. So let's say that's a 5 then. Why can't that be a 5? Ah. So, if this is a 5, that's a 2, that's an 8, that's a 6, which is a contradiction there. And that is something that I had a lot of difficulty seeing, because it's not super obvious. You kind of have to bifurcate in order to see that. But I will fill in the rest of the grid. And there we go. Oh, 8332. I'm pretty happy with that puzzle. Didn't take me too long in the end, so I'll call that ultimately a victory.